Dear colleagues, let me introduce the research which is devoted to catastrophes, fractals and house in geoengineering and water treatment systems. This research was realized at Tavrida National Vernadsky University, Kiev, Ukraine by Igor Yeremeyev, Volodymyr Kyselov, Igor Sikorsky Kiev Polytechnic Institute by Natalya, Remez and Alina Dychko, and University of Economics and Humanities, Poland, by Ievgen Khlobystov. In shallow lake ecosystems, as well as in most artificial cysts formed during the construction of hydroelectric power plants, is an example of a classic catastrophe with several attractors. This is an example of a bifurcation in the behavior of an ecosystem when it gets to the point of return to the seasonal aid. Usually two different states of such shallow water bodies are identified. In the state of the bottom layer, under conditions of high transparency, there is a vegetation ecosystem in the bottom. With an increase in the intake of biogenic components of wastewater, turbidity of the water increases in the ecosystem crosses the catastrophic threshold and transforms into a hypertrophic turbid phytoplankton ecosystem in bottom sediments. In reality, there are lakes that regularly pass from one state to another, as Lake Ontario in North America, for example, regularly experiences similar cataclysm. In some water bodies, the beginning of spring determines the state of the ecosystem in summer because of loading of biogenic components. Its projection into the parameter's value axis has some peculiarities. When the parameter changes, one of the stable equilibrium position disappears, merging with the unstable one, and the system is forced to jump to a new regime with sharply different characteristics. Thus, the problem of accessing the actual state of the geoengineering complexes that are part of water treatment systems can be considered as a procedure of finding the maximum safe band stress, for which it is possible to use the data of a set of measurements, observations, or features studied in order to the state of structures as or one or another cluster. The first step in the assessing procedure is to define a scale of states, where 0 corresponds to the absence of any problems, 4, for example, to an emergency state requiring destruction and reconstruction of the structure. All intermediate classes of states provide appropriate recommendations for repair and restoration work. The amount of physical wear is associated with the cost of indicators to the structure. So, with an increase in physical wear, the initial cost of the structure decreases by the same percentage. Considering the fact that overhaul eliminates physical wear to a certain extent, there is an economic feasibility to overhaul if the cost of the repair does not exceed 40% of the primary cost of the structure. If to take the numerical form of expressing the intermediate diagnostic state of the form, for example, of the function of membership to the corresponding problem requiring major repairs, and to interpret the values of the estimation truth in the following form: 0 not true, weak level of truth, and so on, it is possible to use the following scoring rule. If the number of cracks Cn is estimated at the level 0.3, or the presence of large cracks Lc at 0.2, or excessive deformation of structural elements at 0.1, then the overhaul of the Cn is not needed. or if Cn is estimated at 0.6 or Lc is at 0.5, or deformation of structural elements at the level of 0.5, then overhaul of the Cn is necessary. And belonging to the state of corresponding to the need for the overhaul is estimated as maximum of the set of such states. Another approach is also possible. Let we have a set of x, y, and z, then demonstrate the further relation of R, further relation of S, and further relation of R and S, where we have x a set of signs, y a set of types of potential damages, and z a state of sewage damages.